Attendees are in listen-only mode.
Hello everyone, I'm Gail Warren with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Elizabeth Weitzel, Jordan Dentz, and Eric Antonelli joining us today to talk about effective use of central heat pump water heaters and control systems to reduce the energy use in hot water distribution. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. If you have technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you would like to ask a question, please use the questions pane to type in your question. And if possible, please indicate to whom your question is addressed. If you are having trouble viewing the materials through the webinar portal, you may find PDF copies of the presentations at the website listed here, and you may follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting program prepared for you today that will focus on the effective use of central heat pump water heaters and control systems to reduce the energy use in hot water distribution. Before our panelists begin, I will provide a short overview of the Building America program. Following the presentations, we will have a Q&A session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. Building America uses applied research to deliver building science solutions using a 4-step framework. These innovative solutions are tested in homes to develop proven case studies of success the market can point to. Building America provides the tools the building industry needs to ensure the innovations are applied correctly, always keeping an eye on energy performance, durability, quality, and affordability. The final step, infrastructure development, is the conduit to getting innovations to the marketplace. Building America research focuses on how the components of new and existing homes work together through systems integration. As the market changes and evolves, so has the direction of our research in order to add value and drive changes in performance across the building industry. In addition to technical challenges we have been addressing for decades, there is now a need to understand market transformation issues such as evaluation of energy efficiency. In the 20 years of Building America research, we have spearheaded combining ultra-high efficiency with high performance in both new and existing homes, and we are consistently achieving this challenging task. For example, in 1995, a typical home used 3 times more energy per square foot compared to today, and indoor air quality, comfort, and durability problems were common. Today, a home built to DOE Zero Energy Ready Home specifications uses less than half the energy and is more comfortable, healthy, and durable. By 2030, Building America will demonstrate the new and existing homes can produce more energy than they use. Do you want to know more about these proven innovations? The Building America Solution Center is your one-stop source for expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. You can find it by the URL on your screen or by searching on Building America Solutions Center. Also, the Building America website provides information about the program, the latest top innovations and case studies, and there you can also subscribe to the monthly newsletter. And now on to today's presentation. Our webinar today will provide information about improving efficiency of central heat pump water heaters and control strategies that can reduce the energy use of hot water distribution systems. If you would like detailed information about any of these efforts, or if you are interested in collaborating, please feel free to contact any of our presenters. Our first speaker today is Beth Weitzel, who is a senior engineer at the Davis Energy Group, the lead for the Building America team, Alliance for Residential Building Innovation. Today, Beth will share the results of an evaluation of a 10.5-ton central heat pump water heater installed at the UC Davis West Village Zero Net Energy Community, which is one of 45 similar units installed in student apartment buildings at West Village. The heat pump water heater was monitored from October 2011 through February 2013 and provided useful information to the developer and installation contractors as they worked through early issues in implementing a technology new to them. Our next presenters are Jordan Dentz and Eric Ancinelli from the Levy Partnership, the lead organization for the Building America team, Advanced Residential Integrated Energy Solutions. Jordan is the vice president at the Levy Partnership, where he develops and manages building science research projects and consults for building owners and developers. Eric is a mechanical engineer with expertise in steam heating, specializing in energy auditing, modeling, and consulting. Jordan and Eric will summarize the results of a field study in which two types of central domestic hot water system controls, demand control and temperature modulation, were retrofitted into 4 existing multifamily buildings in New York. They will describe energy and cost savings and resident satisfaction, as well as interactive effects with space conditioning systems. With that, I'd like to welcome Beth to start the presentation.
Thank you. So today I'll be sharing the results of a field evaluation of a 10.5-ton heat pump water heater that was installed at the University of California, Davis's West Village student housing. But before I go any further, I just want to add the disclaimer that the results presented are not representative of certified rated testing conditions, that they are field performance data, and the conditions in operation is different than those used for performance standards. So with that in mind, we'll continue on. In the background, I'll lightly go over the history and reasons for central heat pump water heaters, the site project, and system configuration. Our objectives for the project were to measure the field performance and reliability of a central heat pump water heater, most notably how often the heat pump water heater meets the load, and under what conditions does it need backup. We then wanted to compare the economics of running the heat pump water heater system to conventional electric storage and natural gas storage options. I'll go over the observations we made during the monitoring period and how we took the monitoring data and developed a heat pump water heater model in Transcript to perform the economic comparisons. So why heat pump water heaters? According to the Department of Energy, more than 40% of U.S. households use electric resistance water heating. There have been extensive studies on single-family homes that have demonstrated that heat pump water heaters can provide 50% or more energy savings compared to electric resistance. There's been less attention on multifamily heat pump water heating, however, as the product options are more limited, and at the time of this study, there have not been many central heat pump water heaters installed and monitored. Most multifamily units typically use a central storage or boiler system or have distributed water heating. So the project install that we had the opportunity to monitor was at the University of California, Davis at a site called West Village, which is a mixed-use commercial and student housing complex. The site's located in Davis, California, outside of Sacramento, which is a specified hot, dry climate. And while in California natural gas service is more typical, West Village is a targeted zero net energy community, and it was planned to have enough PV to supplement all electric service to the site, as well as having advanced items like a biogas system that worked on agricultural waste. There are 45 student apartment buildings, each with 12 units. The building that we monitored had 36 bedrooms, but there's about 2,000 individual bedrooms on site. The buildings are 14,200 square foot and served by a 10.5-ton heat pump water heater with electric resistance backup. The backup what consists of two 120-gallon electric resistance heaters that are 54 kilowatts each. The building was also served by a recirculation pump that was both temperature and timer controlled. So this is a system diagram of our installation. Cold water, you can see my mouse here, enters the building from the service and mixes with the recirculation loop and branches to both the heat pump water heater and the first storage unit. The heat pump water heater is a direct heat exchange with the first storage tank. The supply from the first tank then goes into the secondary tank, and then finally to the building supply after a mixing valve. Our sensors were placed to capture the total heat pump energy delivered, domestic hot water energy delivered, recirculation losses, and total electric energy usage.
Beth, this is Heather. Sorry to interrupt. Do you have your control panel? Thank you. You fixed it now. Thanks. We needed your control panel closed to see the whole thing. Thanks so much.
Oh, sorry. Our period of monitoring began in October 2011 and continued until January 2013 so that we could collect at least a full year's data after the initial commissioning phase. So while monitoring was intended for documenting the field performance of the unit, active monitoring became very handy during commissioning. When we installed our sensors and began collecting data, we immediately noticed that the system was not operating properly. The compressor was running, or the compressor was not running, and all the domestic hot water supply was being delivered by the electric resistance elements. The field installer did not notice the error because the evaporator fan and circulator pump were both operating continually, giving the sense that the unit was operational. And the only way that they would have noticed is if they had remained nearby for a long period of time to notice that the unit wasn't shutting off. The installers were not familiar with the technology, and the control interface didn't give any kind of immediate feedback or warning light to alert to the issue. Another issue that was noticed was the temperature feedback for the heat pump was low, and it was determined that a sensor was improperly installed in the tank. So we had them fix that during the first monitoring phase. And then the manufacturer supplied recommended temperature settings for the operation to make more use of the heat pump water heater. But we noticed during monitoring that the heat pump cycles were short and frequent, and we suggested different points in order to optimize and extend full load operation. But during this monitoring period, we decided to continue with the manufacturer's recommended settings, and that's reflected in the data that's reported. About 8 months into monitoring, a bearing in the evaporator fan failed, and the unit shut off, defaulting to electric resistance heat. This failure, again, would not have been noticed for a while, at least not until the electric bills were received. But since we were actively monitoring, we reported the failure, and it was repaired quickly. This failure is likely unique and not indicative of typical unit reliability, but it's worth noting that there was not at any time any sort of feedback that would allow the building maintenance staff to recognize that the unit had failed. So later on, the manufacturer installed a service warning light on the panel, and personnel began doing daily inspections. And finally, near the end of monitoring, the controller lost its set points, and the unit again defaulted for electric resistance heat. And so we were still monitoring and were able to report that error rather quickly. There are 45 units in this housing complex, and the findings of this monitoring were shared with maintenance workers in hopes that the other units would be commissioned and operating the same. So this slide shows a full year's data from the end of our commissioning in October through the end of January 2013. Now, student occupancy is atypical to normal multifamily occupancy behavior. Students often have long daily schedules and are absent during observed holidays and breaks. As you can see, the demand drops down significantly during the Christmas break and reduces again during the summer. In the tail end of monitoring, you can see where the heat pump water heater had shut off due to its lost set points. And it took some time for the building maintenance staff to respond because it was during the Christmas break, and when the sessions resumed again in January, other maintenance items took a little higher priority. In the second chart, you can see the difference in energy consumption is related to the demand for both electric resistance operation periods and the heat pump water heater operating periods. There's almost 2.5 times the amount of energy used when we defaulted to electric resistance as compared with the heat pump. The data from the monitoring period was then compiled and filtered for full load operation to determine the relationship of capacity and power to both entering water temperature and outdoor temperature. The relationship was developed using linear regression, and the resulting map was formatted in such a way that we could use it with Transcript model for simulations. Transcript is a transient simulation suite. The map is slightly limited in that the entering water temperature was on average 125 degrees, and the flow rate was 20 GPM, conditions that are different than the standards ratings. So the Transcript model using the monitoring performance map was developed to ultimately perform a full year simulation and then run in various climates. The model is structured very similar to the plumbing structure of the system, but different heat pump water heater models were used to simulate both startup conditions in which the capacity is degraded, freezing lockout in which the compressor would be shut off, in this case it was 32 degrees, and evaporator fan modulation that was observed at high outdoor ambient conditions. The heat pump controls from observations as well as from literature were programmed into the model, and a simple building structure was used to supply the ambient condition for the storage units, which were located inside of a service room. The model was first validated using weekly sample data from both the winter and summer sessions, and then transitioned to a full year simulation using a typical hourly demand profile from the ASHRAE service water heating guidelines. When the annual simulation was performed in various climates, the hot water demand was varied slightly to account for the variation in distribution losses. So finally, the annual simulations were then run, replacing the heat pump water heater with typical electric storage and natural gas storage models. The electric storage model was a multiple node, it's 8-node model that used the same ratings from the storage units observed in the field. The natural gas model is a similarly sized unit with a nominal 80% efficiency. The climates compared include hot, dry, Sacramento and Phoenix, hot, humid, Houston, cold, Denver and Chicago, and marine, Seattle. The annual operation costs were compiled using the state average utility pricings for electric and natural gas as reported by the U.S. Energy Information Administration. In all cases, the heat pump shows significant operation cost advantage over the electric storage units, between 49 and 59%. Now, the incremental cost of this installation was about $500 per apartment, though in this case, as we were told from the developer, by going electric, there were additional infrastructure cost savings by not having to supply natural gas and venting, as well as freed floor space from not having individual unit heaters. So they told us for this installation they assumed a zero incremental cost. So this chart here shows just the operational cost comparison. But if we were to assume a $10,000 incremental cost relative to a central natural gas system, the annual savings would have to be about $1,000 in order to get a payback of 10 years. And that doesn't include utility or state rebates. So in climates where natural gas is both readily available and cheap, this could pose a problem. But in many climates where electricity is expensive, more expensive, the unit operation is more favorable. To give another view, this map shows the ratio of natural gas cost to electricity. In the green zones, natural gas is less expensive than electricity, assuming 2 COP heat pump as the transition point. And the blue zones show that heat pump water heaters would be more effective. So for instance, while Georgia, Tennessee, Oklahoma are more favorable to heat pump water heaters, Alaska and California are more favorable to natural gas. Alaska definitely because it's cold. The areas in white did not have natural gas rate data from the EIA. So in summary, we noticed from monitoring that the system performance was impacted significantly by cycling. A lot of degraded performance from the cycling, especially during the summer when occupancy was low and there was a lot more parasitic losses. But it was also impacted by lower flow rates and the higher inlet temperatures from the recirculation loop. We suggested that either a deadband be widened or the controls changed some to improve and extend full load operation, but maybe even going to a 2-stage heat pump water heater would improve that performance. Installation and training is critical. These contractors had not had much experience with heat pump water heaters, and there was not at the time adequate feedback to alert maintenance of unit failures. That was later remedied. But had the unit been in service and not monitored, it would take months for operators to notice the failures in the utility bills. So the unit was sized properly to meet the load. There was very little electric resistance usage. And it fits with some of the normal recommendations for single-family homes. And finally, the savings are most significant in areas where electric costs are higher than natural gas. And cheap natural gas can prove a challenge with the higher installation costs of these units. So with that, thank you for your time, and I'll pass on to the next presentation.
Next up are Jordan and Eric.
Okay, thank you very much. This is Jordan, and let me go to the beginning of the presentation. Okay. All right, thank you. Let me minimize this. Okay. So we're going to be discussing a variety of control systems for central domestic hot water systems, and a field test of 2 control strategies in 4 buildings in New York City. The research was sponsored by the Building America program as well as the New York State Energy Research and Development Authority. and lead research team with the Levy Partnership and CDH Energy. So I'm going to provide the introduction, and then Eric's going to pick up for the balance of the presentation. So just some background, energy consumption for water heating in multifamily buildings is a significant share of site energy use, nearly 20% nationally, according to the Energy Information Administration. And energy efficiency of central water systems in multifamily buildings can be very wasteful. This diagram shows for one of our sites, and this is typical of other sites that we've looked at and others have studied, that perhaps only half of the energy that is generated at the water heater actually reaches the end user as useful energy. The rest is lost to either boiler losses, standby losses, recirculation losses, or other losses. To provide some context, the central recirculating domestic water systems are common in multifamily buildings. Often the recirculating pumps run 24 hours a day, and many times without any sort of control. And that increases energy consumption in two ways. The primary way is that heat recirculating, hot water recirculating through those lines loses heat to the surrounding environment through radiation. And minor energy loss is also due to the pump energy, which is running continuously. So why do we have these systems? Primarily to reduce wait time at the tap for users. You can see this diagram. The two diagrams here show typical systems. With a water heater, there is a supply line and then a return line that brings it back to the water heater. And that pump keeps the lines hot so that wait time at the tap is minimized. So there are four major types of controls, and I'll just review quickly each one. Timer controls, which Beth mentioned in her presentation, are a simple time clock that turn the recirculating pump on and off according to a time schedule. And generally the time schedule should approximate peak periods when water pressure will provide the flow. When a user demands hot water during an off period, however, they're going to have to wait until water reaches the end use, reaches the point of use. Temperature control is another form of recirculating pump control, and it automatically turns the pump on and off based on a temperature set point, usually around 120 degrees, with a sensor on the return line. So this will use less pump electricity because it turns the pump off, but it won't do much to reduce the radiative losses from the pipes because the pipe temperature will remain at 120 or whatever the set point is. A third type of control is temperature modulation control. And this doesn't control the pump, but it controls the supply set point. And based on a schedule, it increases the supply temperature during peak times and reduces it during off-peak times. So energy can be saved by having a lower overall water temperature and reducing the heat loss through the pipes that way. But the pump does run continuously. Finally, demand control uses, it's a newer control strategy, in one that we tested in this study. It uses two pieces of information, real-time user demand based on a flow switch installed in the makeup water line, and return water temperature at the pump. And the pump will only run if there is demand and the temperature at the return is below a set point, typically around 100 degrees. Furthermore, the pump will run if it's been off for 5 continuous hours. I'm going to turn it over to Eric to discuss our project.
Thank you, Jordan. So we set out with this research project to answer several questions. We wanted to know how the control strategies of temperature modulation and demand control would compare to constant pumping and to each other in terms of pure energy savings. We also wanted to see what the cost effectiveness of this would be as a retrofit to a multifamily building. And we wanted to also estimate and include the interactive effects between the DHW energy savings and the heating and cooling loads that we'll talk about in a little bit, and how that might diminish payback somewhat or not. Finally, the potential complications, we were hoping to identify and resolve in doing these installations and in testing these controls, any kind of problems that would occur to make sure that they're working well. So previous research, there's a good spread of temperature savings, of energy savings attributed to the controls, and they generally range around 10–20%, with some higher than that. So here's a quick profile of our 4 buildings that we installed the controls in. You can see we had data collected over all 4 seasons at all the buildings. 3 of the 4 had storage tanks, and 1 had a tankless coil that ran through the space heating boiler and sent hot water to the mixing valve. And we'll talk a little bit about mixing valves towards the end of the presentation. Typical size buildings. And one other thing to consider, these are all, again, in the New York City area. It's a heating-dominated climate, and that has 2 effects. That both for the space temperature interaction and also the incoming makeup water temperature varies quite a bit seasonally. And there's also some wintertime increase in usage. That's just the behavioral thing among tenants, and that increases fuel consumption. So here's a typical schema from one of the buildings showing where we installed temperature, flow rate, and equipment runtime sensors. And actually, there's a tiny mistake there. This is the building. We had an electronic mixing valve. It says mechanical, small plug. So the 2 test strategies, demand recirculation and temperature modulation. These were run in succession for a period of 1 to 3 weeks apiece, continuously rotating along with the baseline continuous pump operation over, again, 4 seasons. And you see there in the description of the temperature modulation controls, we had a peak temperature of 125 degrees Fahrenheit and an off-peak temperature of 110. And I have peaks in quotations because we'll see in a few slides that the idea of peaks and off-peaks didn't come out quite as we had assumed. And I'll discuss that a little bit. These 2 graphs illustrate the point of varying consumption over the winter and summer seasons. So you can see in the top left, the makeup water temperature coming from our surface water reservoirs in upstate New York varies by quite a bit, about 30 degrees Fahrenheit from summer to winter. And also in the bottom right graph, you can see that gallons per day per bedroom roughly increased by 30–40% from summer to winter, and that's behavioral. Can you go back one, actually? Sorry. So in order to account for when comparing the baseline to the continuous across these 4 seasons and to the test controls, we wanted to make sure we were measuring fuel savings attributed to the controls and not to these effects. So we normalized the boiler runtime data for 3 parameters: the gallons of DHW consumed per day, the incoming cold water temperature from the city mains, and also for the DHW supply temperature that was being sent out to the building occupant. So for some results. First, the installed costs. These are the actual costs at the buildings where we installed the controls. For demand recirculation, it was approximately $3,000. And for temperature modulation, it ranged from $2,000 to $5,300. If you already have an electronic tempering valve, an electronic mixing valve, on site, that can reduce the cost of temperature modulation control, obviously. And again, half of this was due to labor, and that can vary. So here we have the supply and return temperatures for all 4 buildings for all the test cases. And this is what's going to drive any kind of savings that you'll achieve, either in reduced temperature at the tap or reduced radiative losses along the recirculation piping. I think there should be two of these for temperature modulation. We set set points of 110 and 125 degrees, and these are obviously well above that, and that brings to bear some commissioning issues that we'll talk about in a little bit. And this obviously, there were some savings associated with these 2 buildings, but not as much as could have been optimized. So the recirculation pump runtime with demand control was reduced substantially and consistently. This is a good thing. The pump control had the pump running 15 minutes a day. That saved several thousand kilowatt hours a year, even with a fractional horsepower pump. And at local energy prices, that's something several $100s a year. These are the measured fuel savings at our 4 test sites. And in the top row, you can see the typical range of baseline fuel consumption for the buildings. And the fuel reduction range across the 3 strategies from maybe 6 to 15%, with the exception, again, for those 2 buildings where it was only about 2%. Now, before looking at the financial payback for these fuel reductions, we wanted to account, again, for the space conditioning and attractivity. And we, rather than going with a model where there'd be more assumptions and more room for error, we wanted to do something simple. And knowing that the interactive penalties or bonuses would be some fraction of the DHW energy reduction, we simply applied best and worst case scenarios that gave a reasonable range and conservative range of heating penalties and cooling bonuses based on the average typical weather for our region and the typical efficiencies for the HVAC equipment. So for the central scenario, about 1/3 of the DHW fuel reduction was considered a potential heat penalty that reduces the total savings. Cooling bonus, again, the different units, kilowatt hours versus therms, all the buildings were natural gas, comprised about 10% of the total dollar savings. And maybe somewhat counterintuitively, the reduced pump electric contributes a substantial amount to the dollar savings, about 1/4. So let's take a look at the simple payback. Here you can see for the 4 buildings, annual costs, including the recirc pump electric, range from about $10,000 to $30,000. And now inclusive of the interactive effects, the cost savings on an annual basis averaged about 9% for demand controls, only 3% for the temperature modulation, and 12% for both combined. And in the worst case scenario, for the interactive effects that we showed in the previous slide, you're still getting less than 4-year demand payback for demand controls, which is pretty good, and 21 years for temperature modulation, which is not so good, especially considering these controls are typically said to have a useful life of maybe 15 years. Now for the conclusion, for the next few slides, we'll take a look at some of the take-home lessons that we learned in conducting the study. So demand profiles. We found this very interesting, very counterintuitive. This relates back to the utility of temperature modulation control, which relies on the assumption that you're going to have pronounced peak periods in the morning when everybody's getting ready for work, and in the evening when everyone comes home and cooks meals. And you don't see that, and these are typical graphs, and we looked at a lot of 24-hour draw profiles across the 4 buildings. if anything, there's a period of low consumption that tends to happen for a few hours in the early morning. And so this somewhat defied temperature modulation as a strategy. And it's possible that using the constant lower bound temperature satisfied people using their hot water at all points during the day. Commissioning. This was another important take-home, something mentioned briefly in the previous presentation. So these three graphs show temperature modulation, typical 48-hour supply temperatures for the three buildings where we installed these controls. And what's happening in the first graph for Site A, you can see that the lower bound is indeed hitting that 110 and 125 degree set point that was programmed into the control, but for some reason the boiler is responding to a 20, 30 degree differential and raising the temperature well above that. And of course, the average temperature was skewed up and the savings were diminished. For Site B, this is the building that had the mixing valve and not a storage tank, and it looks like it did a pretty good job of maintaining the desired temperature set points. At Site D, again with a storage tank, the lower bound temperature seems to have been met, but the upper is skewed well above 125 degrees, and this diminished savings. This graph reiterates and illustrates that correlation between boiler runtime and makeup water temperature as it varies over summer and winter. And you can see a strong inverse relationship here. So to sort of bring this back to the prior studies that we found in our background literature, we've shown about an average of 9 to 14% fuel savings from the demand and demand with temperature modulation controls, respectively. Prior studies showing somewhere in that range, plus higher, with demand recirculation. But again, they didn't account for interactivity, and that might be, responsible for some of the effects you're seeing here. Another common concern that we frequently hear is that non-continuous flow that you'd have with the demand control does not work with mechanical mixing valves. And this is a popular local brand will actually even void the warranty if you install demand recirculation controls. The idea being that the non-continuous flow will stress the valve to the point of failure. And with electronic mixing valves, the strictures aren't as severe, but there's still this risk that after a period of stagnant flow, when the flow resumes, there's a potential for hot boiler water to be sent through the valve to the tap at dangerous scalding temperatures. But there's ways to address this. There's several manufacturers that produce mixing valves that are approved for non-continuous flow. And there's also this idea of a dummy recirculation loop, which we haven't tried yet. But the idea would be to take a very small pump and install a small recirculation loop that runs just in the boiler room, doesn't incur much of a energy penalty, but allows the valve to see continuous flow. Speaking to the electronic mixing valve issue of potentially sending out dangerously hot water with non-continuous flow, we didn't have fine enough data. We had 5-minute average temperatures to look at, where we are going to take maybe 10 seconds interval data and get a better picture of this. But you can see here that both with continuous flow and with the demand recirculation pump controls, you're getting temperatures that are well above that 125 degree set point. So something we'll be looking at in the future. Another possible issue that was presented to us is this idea that with a storage tank and demand recirculation controls installed, you can potentially send very hot water at irregular intervals to the supply pipes. So the top graph, these are both from the same building. These are both supply temperatures coming from the tank. You see this signature sawtooth pattern, and that's characteristic of the tank water being mixed by the recirculation pump that's operating continuously. So you can see it steadily declines as more and more makeup water is added before the boiler fires. And in the bottom graph, this is what you'd find with either no recirculation system in place at all or with the demand controls that are running the pumps very infrequently. You get more of a flat plateau. And this is because the water in the tank is stratifying. The hot water is coming in from the boiler to the top of the tank. It's less dense and it's staying there at the top of the tank. And as the makeup water, which is more dense, comes in at the bottom of the tank, it stays at the bottom. And without the pump to circulate it back and forth, as the tenants draw water, it comes from the top of the tank. And the issue here is that because the aquastat is placed fairly far down the tank, it might sense cooler temperatures with demand-controlled pump and call for the boiler to run, and the boiler might send hot water to the top of the tank where it could short-circuit across and go up to the tenants. And we've circled two parts on the plot here which may show that this is happening, but we're going to be looking more at this in the future in our next project that Jordan's going to talk about shortly, and confirm whether this is a prevalent thing or if this is just a one-off. Finally, a word about Legionella. The temperatures that favor Legionella occur probably in every DHW system at some point on a branch or a dead leg. And we're not sure if doing demand and temperature modulation controls in cooling the recirculation loop or in cooling the tank temperatures periodically, if this poses a risk or if this exacerbates that. Now, government agencies are split on the issue, with OSHA discouraging demand control specifically. Other agencies require it. And more research is needed specifically to domestic hot water systems. To conclude, an important piece, thermal comfort or occupant comfort, all the controls are implemented without complaint. And to be specific, over the 4 buildings over the year monitoring period, we did have 1 complaint to the super that was registered, and he didn't make any adjustments to the controls, and the complaint didn't come back. So we take that as a pretty strong indication of comfort and satisfaction, because people will let you know if they're not getting hot water to take a shower. Also, as I said, the draw profiles, the demand profiles, didn't show the pronounced peaks and troughs of on-peak and off-peak usage, and that may indicate that a constant lower temperature would be ideal in place of a temperature modulation strategy. The cost depended on the existing configuration of the building, but even then the paybacks for demand control were favorable. And again, this scales with building size and also fuel type. These buildings were using natural gas. More expensive fuels would make the payback more favorable. Jordan?
So I just wanted to mention that we're continuing to work in this area, and we're moving forward with a rollout of 40 buildings to install demand controls only. This is sponsored by NYSERDA, and we'll be also looking at optimizing supply temperatures and those electronic mixing valve issues that Eric mentioned. So if there are any buildings out there in New York State that are interested in participating in this, please let us know. And that is the end of our presentation. Thank you.
Okay, thank you for those outstanding presentations. We have time now for a few questions. We already have some great questions from the audience, and you may submit additional questions through the question pane on your screen. Our panelists will answer as many questions as time allows. And we have several questions here for Beth. I'll I'll go through those first. The first one is, in the modeling, was the demand profile based on the measured data for the student village, or was it a standardized profile?
At first, for the validation part of the modeling, we used profiles from monitored data. But when we went to the annual comparisons, we went to a standard draw profile that was informed by the ASHRAE service water heating guidelines.
Okay, the next question was, how many apartments were in the monitored building and how many people lived there?
12 apartments and 30.
I'm sorry, could you repeat that please, Beth?
Sorry, can you hear me?
Yes.
12 apartments and 36 occupants.
Okay, and then another question is there a recirculation loop that serves each unit or only one central loop?
One central loop.
And then a couple of more questions. What were the steps in the model validation effort?
The model validation effort, we started with developing a performance map, and then we built the model and ran it with sample 1-week monitoring periods in the spring and the summer, or in the winter and the summer. And we compared that against monitored data and drove it down to less than 1% of variation.
Okay, and what level of field COPs were observed and how did it vary seasonally?
We saw monthly average COPs of between 2 and 4. The lower happened mostly in the summer where there were higher parasitic, lower loads. And since there were lower loads, there was a lot more short cycling, and so the performance was degraded.
Okay, thanks. And now I have several questions for Eric and Jordan. Have you looked at the overall energy impact of the best central system compared to water heating in individual units?
That was not part of this. To compare individual unit water heaters with central water heating systems was not part of this study. This was primarily a retrofit-based study. So that probably would not be within a normal retrofit scope unless there was significant problems with the existing system. But no, we did not look at that in this study.
Okay. Was there an increase or decrease in tenant satisfaction with demand control?
So, like we said towards the end of the presentation, there weren't any formal complaints. We also surveyed the tenants, you know, in addition to periodically checking with the superintendents. And what we found was there weren't any complaints attributed to the demand control, but some people found temperature modulation, what would you say? They didn't really like that the hot water temperature fluctuated throughout the course of the day. And it wasn't, so we didn't call that a hard complaint, but seemed to reduce satisfaction somewhat, the temperature modulation specifically. I don't think demand control yielded any dissatisfaction. And of course, there's the question, you know, the fellow who has to wake up at 4 a.m. to be at work very, very early, the first person that's going to take a shower when the pump has been off, presumably for some time, up to 5 hours, how long does he or she have to wait for the water to get hot if the pump's pumping something like 20 gallons per minute? We don't have data on that, and that might be something we look at in the next project. But again, no formal complaints.
And the next question is, what was the typical flow rate for demand control pumps?
So we spot measured this a few times at the buildings, just at the beginning of the study. For the flow rate of the recirc pump, I think somewhere between 12 and 22 GPM, depending on the building.
And then another question, were domestic hot water distribution pipes insulated in the New York studies on the 4 buildings?
One of these was, oh, sure.
Well, 2 of the buildings, all of the buildings, the loops, the piping in the basement, the exposed piping was insulated. The risers in 2 of the buildings, buildings A and B, were not.
They were a little older.
They were older buildings. In buildings C and D, those pipes were well insulated, and it was only a 3-story building, so the risers were not recirculating. And that might explain, partially explain the lower savings in buildings C and D. Those pipes were, the recirculation loop was entirely insulated in those buildings.
Okay, if my building participates in this upcoming study, do we get to keep the controls after the study is complete?
Yes. Yeah, the study is structured so that the buildings pay half the cost of the installation and labor, and we would monitor the performance for a couple months following installation, and then use that data for the study, and the building would retain the system.
And then another question, what kind of flow sensors did you use, and why does per bedroom usage increase so much in winter?
Flow sensors we used.
We used a few different types of flow sensors. So there's the flow switches, which are part of the demand control system, and that's a simple switch. It's not it doesn't measure the flow. That's provided by the manufacturer of the innovative demand control system. And then to measure flow, we use 2 different types of systems based on the size of the pipes. We used an ultrasonic flow sensor for the larger buildings, and for the smaller buildings, we used omega flow sensors. And then, Eric, do you want to address the increased usage in the winter?
Sure. So we think, and in doing some of the literature, this seems to come down to behavioral usage. People taking longer showers because it's colder outside. No firm answers. It's a pronounced trend on the graph. You can see all 4 of the buildings showing that similar phenomena. But
that does have implications for utility bill disaggregation, though.
Sure. And again, heating dominated climate. It'd be interesting to see in a warmer climate how that would look.
And then another question, can you repeat the primary reasons why you believe the buildings in your study got less savings from the demand control than past studies reported?
The primary reasons probably came down to, part of this could be the supply temperatures that were sent up to the building. To have 44% savings from demand control, I sort of struggle for a reason as to how you could lose so much of that energy from the incoming fuel energy just to the demand recirculation loop. It could be a different configuration in the building with a recirc loop that runs a primary loop in the basement and secondary loops that branch all the way up to the top of a very tall building. I'm not sure. But the difference attributed between our 9 to 12% and the other lower estimates, 10 to 20%, I would guess interactive effects. The other studies did not look at interactive effects. with space conditioning.
It's also, I should point out that all the previous research on demand controls that we researched as part of our literature review were in California. So the buildings and the climate quite different than what we worked with here. We have older, larger, or taller buildings with different types of mechanical systems generally.
Okay, those are all the questions we have for now. Panelists, before we take our quick survey, do you have any additional or closing remarks you'd like to make before we close the webinar?
Nope, none here.
Nope.
Thank you.
Listening.
All right. Okay, we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us to know what we are doing well and where we can improve. The first question asks whether the webinar content was useful and informative. To answer, click on the radio button right in the GoToWebinar panel. The second question asks about the effectiveness of the presenters. And the third question asks whether the webinar met your expectations. Thank you for taking our survey. Stay tuned for the next Building America webinar scheduled for February 12th at 3 p.m. Eastern Time. The webinar topic will be Part 1 of High Performance Enclosure Strategies for Unvented Roof Systems and Innovative Framing. Registration will soon be open on the meetings page of the Building America website. On behalf of the Building America program, I'd like to thank our expert panelists for presenting today and our attendees for participating in today's webinar. We've had a terrific audience and we appreciate your time. Please visit the Building America website to download a copy of the slides and learn more about the program. We also invite you to inform your colleagues about Building America resources and services. Have a wonderful week, and we hope to see you again at future Building America events. This concludes our webinar.